I decided to do one extra example, a bonus one. So this is going back to the friction chapter, 6.1. It says, in the figure, a block of mass m is 3.0 kilograms, slides along a floor while a force F of magnitude 12 newtons is applied to it at an upward angle theta. The coefficient of kinetic friction between the block and the floor is mu sub k is 0.40. We can vary theta from 0 to 90 degrees. The block remains on the floor. What theta gives the maximum value of the block's acceleration magnitude, A? Right, this is a fairly long one, so rather than trying to get all my work in on the whiteboard, we're going to try sharing instead my work already written out. So I do want you to think about this problem. I'm going to even suggest to go ahead and pause the video and work on your own and see how far you can get on this problem. And then you can compare notes with the solution in just a moment. But if possible, please do take the time to figure out how you'd approach the problem, get as far as you can, or at least get the setup done. And then let's check out the solution. So go ahead and pause now if you haven't already. Great, did you do that? I'm gonna trust yes. Okay. So now we can see, here's my solution where I've drawn the box first with that force acting on it, F. And then I also drew in the force of gravity, which I just wrote as mg, the normal force pointing up, and that is up from the surface, perpendicularly up. It's a surface interaction. The other surface interaction we have is the force of kinetic friction, which is going to be opposite the push, or this applied force F. So it's going to be along that surface, but going opposite the applied force. And I wrote down what we know, right? Mass, the applied force, coefficient of kinetic friction, angle can vary between 0 and 90, and the block must stay on the floor. So we could continue moving along here. What do we want to know? We want to find theta for maximum A, acceleration. And this is the key. If you want to maximize a quantity, the maximum, think back to calculus. If you looked for a max or a min of something, the maximum always occurs at the point where the derivative is equal to 0. So if we vary theta in between 0 and 90 to all the possible values, there should be a value of acceleration that is the highest when that function is equal to 0. So when the derivative of acceleration with respect to theta is equal to 0, we can solve for what theta that is. So how, or what tools do we have? Once again, Newton's second law comes into play, F equals ma, and the derivative comes into play. We get to use our calculus, awesome. Finally, our equation for our friction, kinetic friction, is the coefficient of kinetic friction times the normal force. Note, friction as a force is not just the coefficient. We need to have the normal force in there, or else it's just meaningless. All right, now that we've set this up, we can go back to our forces as we've identified them, and we can put them into a free body diagram. So a free body diagram is just going to be taking those same forces and drawing them with the block now as a dot, adding in our coordinate axis, positive x to the right, positive y up, as well as adding an acceleration, that the block is going to be accelerating to the right in the direction of this applied force. And that will be purely horizontal because we know the block stays on the floor. So it's not going to be flying into the air or sinking into the ground. Right, now one thing we will need to do, we've gotten the normal force, the force of friction, mg, all already purely in the x or the y direction, but our applied force F is not yet. So that's where we can use sine and cosine to get the x and y components of F, to break that down properly, excuse me. All right, so with that in mind, we can now look at Newton's second law in the x and the y direction, right? So in the x direction, F net x is equal to max. So the forces in the x direction are, we're going to have, once again, the x component of this applied force, F sub x, and then it's minus the force of friction, F sub k. F sub x we saw was given by cosine of theta, and then we can minus, subtract out that force of friction, which is mu k times the normal force. And that will be equal to the mass times the positive acceleration. We don't know what that acceleration is. We're trying to maximize that acceleration. We also don't know in this final equation what the normal force is. That's a bit of a mystery to us. So let's keep going and see if we can find out more. We can look at Newton's second law in the y direction, because why not? But also because it's there for us. So the forces in the y direction, we have the normal force is purely up. We have the y component of the applied force, and then the force of gravity, the weight mg is pulling down. That's equal to the mass times the acceleration. There is no acceleration in the y direction, that's 0. So we get that the normal force is equal to mg minus the y component of the force. Y component of the force we already found is F sine of theta. So now we have an expression for the normal force that we can use back over here in our equation that had a normal force and acceleration. So if we plug that in, this mg minus F sine theta, in for the normal force, we have F cosine theta minus mu k times mg minus F sine theta is equal to mass times acceleration. We want to get acceleration on its own, so we can divide both sides by the mass. And so we get this expression for the acceleration, that the acceleration is the applied force divided by the mass times cosine of theta minus mu k times g. Notice the mass is canceled in this term. That's nice. Plus mu k times the force divided by m times sine of theta. That's a lengthy expression, but it's not terrible. What we're going to do is we want to find where theta produces the maximum acceleration. So that's where we want to take the derivative of that acceleration with respect to theta. So derivative of cosine is a negative sign. We can keep the constants out in front. Derivative of minus mu kg is just 0. The derivative of sine of theta is positive cosine of theta, keeping the constants out in front. So we get to this relatively simple expression, and it becomes even simpler when we remember that we're saying the derivative equal to 0. With the derivative equal to 0, that means we can add this f over m sine of theta to the other side, and we notice that both sides have this force divided by mass. So we can cancel that out too, and if we divide the cosine of theta over to the sine of theta, remember sine of theta divided by cosine of theta is tangent of theta. So tangent of theta is equal to mu k. In other words, our angle theta is inverse tangent of mu k, which we know is 0.4, and we get that our angle is 21.8 degrees. In terms of sig figs, we only want 2 for this problem, so that would be 22 degrees. Wow, all of that work, and it ends up, all that we need to know is the coefficient of kinetic friction here. The mass canceled out, the applied force canceled out, the angle just depends on how much friction there is, how strong that is as a force. So that is really, really cool. Here again, we use tangent of theta is equal to sine of theta over cosine of theta. And there we can see the entire solution to the problem. It has all worked out. So there we have an example, once again, of creating a free body diagram using Newton's second law in the x and the y direction, and then working on our algebra, in this case, also pulling in some calculus. So now this is the true end of chapter 6.